Welcome to the Explainer. So, if you've ever felt that absolute frustration of staring at a 300-year-old totally static textbook equation, just trying to imagine how those invisible forces actually work in the real world, well, you are in exactly the right place. Today, we're going to take a fascinating journey through classical mechanics. We'll be transforming those abstract concepts into intuitive, interactive ideas, and we're looking at all of this through the lens of how modern college students are mastering these foundational rules using the virtual lab revolution. Let's get into it.
Here's a quick look at our roadmap for today. First, the foundations of classical mechanics. Second, the first law, inertia and action. Third, the second law, force and acceleration. Fourth, busting common myths with the third law. And finally, the virtual lab revolution. Before we dive headfirst into the heavy calculations and digital simulations, we really have to establish the historical weight of what we're learning here. Newton actually wrote this famous quote in a letter to his rival, Robert Hooke, way back in 1676. He said, "If I have seen further, it is by standing on the shoulders of giants." It's just a brilliant reminder, you know? Even the most groundbreaking foundational physics didn't just happen in a vacuum. Newton literally built his mechanics upon centuries of prior discoveries.
Okay, Section 1, Foundations of Classical Mechanics. To truly appreciate our modern virtual learning tools, we need to do a quick rewind to see where these concepts originated. The journey starts way back in 350 BC with Aristotle. He proposed that objects simply move toward their natural places and, get this, require a continuous force just to keep moving. Quite the wrong assumption, right? Fast forward to 1638, and Galileo makes this massive breakthrough discovery of inertia, realizing objects fall at the same rate. Finally, standing directly on Galileo's shoulders, Isaac Newton published the Principia in 1687. That single publication revolutionized physics for over 2 centuries.
Moving right along to Section 2, first law, inertia and action.
Let's transition from that rich history straight into the fundamental rules of motion. Newton's first law is a classic. An object at rest will stay at rest, and an object in motion will stay in motion unless acted on by a net external force. In really simple terms, motion just cannot change, decrease, or increase without the direct interference of an unbalanced force. If absolutely nothing pushes or pulls on an object, its current state of motion is locked in forever. We can actually break this down into 3 specific types of inertia: the inertia of rest, of motion, and of direction. And you experience this every single day. The inertia of rest is exactly why you end up spilling your morning coffee when the subway suddenly lurches forward. The inertia of motion, that's why you need a seatbelt to hold you back when a car slams on its brakes. Your body naturally just wants to keep traveling forward at the car's original speed. And on a much grander scale, it's why a spacecraft glides so effortlessly through the vacuum of space. With zero friction to act as an external force, it just keeps going.
All right, Section 3, second law, force and acceleration.
Now, let's see how all of this builds into the famous equation that actually governs acceleration. Newton's second law states that a body's change of motion is proportional to the force acting on it, and it occurs in the direction of that force. You probably know it best as F equals ma, or force equals mass times acceleration. Basically, it means if you want a heavier object to accelerate at the exact same rate as a much lighter one, you are going to need to apply a whole lot more force. Now, if you are a university physics student, a traditional static free body diagram representing a traffic light suspended by cables probably gives you a little bit of anxiety. Staring at these complex fixed arrows, like tension vectors pulling up at weird angles and the weight vector pulling straight down, it makes it incredibly difficult to visualize how these forces are interacting dynamically. You have to break the forces down into X and Y components entirely in your head. It's exactly why the old static textbook method can be so incredibly frustrating. And this is exactly why the virtual lab revolution is such a game changer for modern mechanics. On one hand, we've got the old whiteboard method with fixed arrows, where visualizing change is just a total mental chore. But on the other hand, in these new digital environments, you can physically manipulate variables like mass, thrust, and friction coefficients using interactive sliders. You literally watch the force vectors stretch and shrink in real time as the acceleration changes. The static page completely comes to life. So the crucial takeaway here is applying a really reliable system, whether you're working on paper or in a high-tech simulation. Think of this 5-step strategy from university physics less like a boring list to memorize and more like your foolproof survival guide for exams. First up, identify your givens. Second, sketch the situation out. Third, draw that free body diagram for your specific system of interest. Fourth, apply Newton's second law and do the math. But step five is your lifesaver. Check if your solution actually makes sense. Always check your final units. I mean, if you're solving for force and you somehow end up with millimeters per second, yeah, you've definitely caught a mistake.
Which brings us to Section 4, third law, busting common myths. Brace yourselves because we are about to bust a massive myth that trips up even the absolute best physics students. But first, let's lay down the rule. Newton's third law tells us that when a body exerts a force on a second body, that second body exerts an equal but oppositely directed force on the first body. Every action has an equal and opposite reaction. Force 1, 2 equals negative force 2, 1. Simple enough, right?
Well, let me ask you this directly. Think about it carefully. Do these action and reaction forces balance out when objects are actively accelerating? There is this incredibly persistent misconception out there. People think that if an object is accelerating, say a massive heavy truck is pushing a tiny small car, the truck simply must be exerting a larger force on the car than the car is exerting back on the truck. But here is the reality check. The law has absolutely no exceptions for acceleration. Zero. Newton's third law applies regardless of whether the two objects pushing on each other are completely stationary, moving at a constant velocity, or literally doing backflips. The action and reaction forces between those two interacting bodies are always, without fail, completely equal and opposite.
Wait, so you might be wondering, why do things accelerate at all if the forces are perfectly equal and opposite? Well, it's because the forces do not act on the same object. Action and reaction forces act on completely different bodies. The force of a blue object pushing a green object acts only on the green object, and the reaction force of the green object pushing the blue object, that acts only on the blue object. Because the net force on a single specific object is what determines its acceleration, those two forces never actually cancel each other out. They were never balancing on the same body in the first place.
Finally, we've arrived at Section 5, the virtual lab revolution. So we've totally conquered the theories, but how are today's college students actually practicing this stuff without getting totally bogged down in static calculations? Well, gamified learning platforms like Praxi Labs are stepping in with these immersive, totally risk-free virtual experiments. Think about it, you can do an egg drop experiment to physically witness the first law of inertia, all without making a huge mess in your dorm room. You can simulate a literal rocket ship launch, tweaking the fuel mass and thrust to watch the second law play out in real time. Or you can run digital collision simulations to perfectly demonstrate the third law and momentum conservation. It's basically like having a virtual lab partner right there with you, providing interactive guidance every single step of the way. We've covered the history, we've broken down the equations, and we've completely busted the biggest myths of classical mechanics. You know the laws now, so I'm going to leave you with this provocative question. Are you ready to step away from the static textbook, jump into the virtual lab, and actually test these forces for yourself? Knowing the theory is one thing, but dynamic, hands-on application, that is where true understanding really begins. Thank you so much for joining me on this explainer, and keep exploring.